What's going on, developers and creators out there? My name is Erickson. In this video we're going to go into post-processing the data in Matlab. If you're not familiar with this project, it's basically a project that analyzes an FIR filter that is implemented in the Xilinx system on a chip FPGA. In the FPGA fabric you have an FIR filter surrounded by other components that is used to test and analyze that filter, and everything is done from the CPU, the configuration and the data transfer from a FIFO to the DDR memory. In the last video we talked about the bare metal application. In the video before that we talked about how to set this up in Xilinx Vivado. So we look at Vivado, Vitis. In this video we're going to go to Matlab and plot the data, see if it makes sense, if the output of the filter matches what we set the DDS to. Now, since we're looking at the filter, let's quickly look at the filter specification. If we go to Matlab, if you have some other tool, but I've used Matlab to design the filter, and if I go to apps, filter design, and then I'll open the filters that are already designed. So that should be file, open session, and it is available to you if you requested this design. So if you go to Matlab folder, and for those of you who already watched the previous videos, you are familiar with this folder set. So if you go to Matlab, filter design, the FDA extension, it will populate and open the filter that is implemented here, and it's implemented in Vivado design. So this is the Vivado design that we've been working on in the previous videos. It's the same design, and if I can find the filter block, which is right here. So this is the filter. So we're looking at the block design, and we're also looking at the Matlab, which has a specification for the filter. And if we zoom in here, so maximize this window so we can see it better, and zoom in so we can actually see some of the specification, some of the details. So we can see that the filter passband goes to up around 2K. Actually, it's right here. So the passband goes up to 2K, and you have around 500 hertz transition band, and then stop band frequencies are attenuated to -80 dB. So the first thing that we're going to do to test this out and process this in Matlab is we're going to set the DDS frequency to 1 kilohertz, which is within the passband of the filter, and then we're going to go way out of band. We're going to go to around 4 kilohertz, and then we're going to set the DDS frequency of to 4 kilohertz, and plot that data in Matlab, see if the filter is working to the expectation. So let's close this out, and I'll quickly show you how to change the frequency of the DDS in the code, in the C application. So everything is done from a bare metal application running on the Xilinx CPU. So let me quickly look at the code. So if we open the file, and we should see the code. If we go to software, source, main. So if we go to main, we should be able to change the frequency of the DDS using in the main function of the C application. So I think it's the first block of the code. So here it is. So DDS frequency controller configuration. So basically by writing to set the DDS output to 1K. So right now it's 1K. It's writing to a register. So basically you would write to a register in the DDS frequency controller custom IP, and that will change the DDS output frequency. And let me quickly show you how. I don't want to get into details about the DDS, but let's quickly talk about how mathematically how you would do that. Here I have opened Xilinx. Let me show you what document is this. I have a Xilinx DDS compile product guide, and if we go to page 14, so page 14 has other computations required to change the output of the DDS. So what we're doing specifically in my case, you can see F out, which is output frequency, is a function of the clock frequency, the phase increment, and the phase data width, the phase increment data width. And we're interested in the phase increment. So we're going to be computing the phase increment. So basically by knowing the output frequency that we desired, and we know what frequency the DDS is running at, and then we know what the data width of the first phase increment is, we can change the output frequency of the DDS. I have a table here that I can show you. So show you this table right here. So where I have all the details for the computation. So I have the phase increment, DDS, I have the DDS, don't want to change that. So I have the DDS clock frequency, it's set to 25 megahertz, and data width is set to 16 bits, and then the output frequency will be 1000 hertz. So if you punch that into that equation, so if you punch all that information into this equation right here, trying to align things here. So if you punch that information into this equation, you should be able to see a 4 megahertz coming out of the DDS. So trying to move things out of the way here. All right, so let's see if that's clear. So basically, if the DDS output frequency is 25 megahertz and data width is, which is right here, is 16 bit, and the output frequency will be 1000, and the desired output frequency is 1000 hertz. Phase increment will be what you see here, and I'll show you how to quickly compute that in Matlab, or you can use some other calculator to compute that. Now, where do you see all this information? How do I know? So you got to go to Vivado to see that. You can see that the DDS clock frequency is 25 megahertz and the data width of the phase increment register is 16 bit. So let's go to Vivado and look at the output. So let's double click on the DDS. So you can see that the system clock frequency is 25 megahertz and the phase width is 16 bit. So we are good with that. So this is the hardware, but we're not looking at it in this video. So let's go back to this. So we are good there. So our goal is to change the output of the DDS. So set it to 1 hertz, plot the data in Matlab, compute the FFT, and make sure that it aligns with what we expect, and then change that to 4 kilohertz, and see if the signal is attenuated to significantly, or to the point that we can't see the signal at all. So let's go back to let's start running the code. So we come back to our main. So right now we're setting it to 1 kilohertz. So pay attention to this printf. We're going to be looking at it while we're looking at the output of the board. So right now we're setting it to 3, which is what you see here, 3. That's what we're setting the phase increment to, and that should give us 1000 hertz. So now let's go ahead and run the code. So let's go to software. We're gonna go to our development, and if you know me, I script about pretty much about everything. So we're gonna be running everything from Xilinx command line, software command line. So let me bring that to the screen. And we're going to source create project. We're gonna do this again. We did this last video, but we're gonna do it again so we can walk through this very smoothly. So let's control paste. So that's the path where we jump into the path where the script file is located, so we can source it. So let's source the create project.tcl. So by running that, we importing files, creating platform, and building project, and also make sure I've set this two-liner here is configuring the std and std out to UART1. Make sure you configure it to your board. This is specific to my board. You change that if you need to. So that's what we running. That's going to take about maybe say 30 seconds, I believe. And then after that, while that's running, the next thing that we'll do is, just like we did in the previous video, we will initialize PS7, load the first stage bootloader, and download the application to the board. So that's going to be done. Oh, and while it's doing that, let me actually open my COM port so we can see the output of the board. So we're going to do buddy. Serial COM1. I'm very familiar with this. Like I said, I've there's so many times that I memorize all of it. So my board's already hooked up, so this is where we're gonna see the output. Let me play it while it's doing that. Let me arrange this so it's well beautiful that we can all see it. Okay, so we can now run the project. Let's source run app .tcl, so that will run the application on the board. And what will just happen there is that we have a full transaction with the DDS. With the DDS and the whole hardware was enabled, and you have a full filter data in memory. So let's go back to the block. So what just happened is that we have the DDS just put out 1 kilohertz signal, went through the filter, stored in the FIFO, and transferred to the DDR memory. Now it's sitting in DDR memory and everything stopped. What I will do now is I will import this data into Matlab for processing. So let's do that by reading the stuff. First thing that we're going to do, maybe I should clarify this, is we're going to be reading from the memory. So this script right here, it's not the script file. Like I said, I'm very script. Everything is based on script. So we're going to read this memory. This is the location where the first data is located, and then we're going to read about 15,000 samples. So we're going to start at the memory location, and then we're going to go down 15,000 locations down, starting from this location. So let's do that, and then it will output the data to a data.txt. So the data will be stored here, the master folder and the Matlab. So that was from a previous exercise. Let's delete that, even though it will overwrite it, we don't have to. And let's go back to Xilinx command line tool, and let's source that script file. So let's do source, if I can have it spelled source right, source build, come on, not build, read memory. That's my attempt to say read memory. So let's keep an eye on the folder location, see if it actually does what it wanted to do. Oh, enter. Okay, so there it is. So here's the data. This is our signal filter data that was stored in memory. So what we're going to do now is we're going to convert this to integer and plot it in Matlab. So if we go to Matlab, I have a script that does it all, converts the data to integer, plots the data, and then computes the FFT, and then plots the FFT. So let's first import the data. So we're gonna go to home, import. There's other ways you can do it as well. So we're going to go to our folder location, and we're going to be importing the required data. Where is the window? Window. All right, here it is. So we're going to select it all, Control all, and then we're going to set the output type to a string array, and then we're going to go to import data into Matlab. So minimize this window. So we have, let me actually clear my Matlab because I was playing with it earlier. So let me clear that my workspace, and then I'll redo what I just did in a second ago. So let's import data. So in a very clean workspace. So here's our data. And then once we run this script, it will do what I just said. So let's go to editor, run. And it didn't like it. Okay, as always. What didn't it like it? That's weird. That's strange. Well, it was working a few minutes ago. All right, let's debug. This is the fun part, people. This is what we're here for. All right, let's figure out what's wrong. It's gonna make my video way longer than I expected. Let's see we're about 15 minutes into the video, but make sure I see if I can fix this quickly. Data. Oh, okay. So what happened is this is data 1, but I'm calling data. This is because there was data here before I even called before I imported the data. There was some other a variable stored with the name data, so I incremented that by calling data 1. So let's clear that again, and let's go back to our import window and then call this data. So that's all good, and then we're going to make sure it's the type is string array. Any other type will not work with the script file. Import data. Again, there's so many other ways you can do it. I'm doing it this way, but you can automate it by by importing data here in scripts, but I'm just doing the old-fashioned way. So we're going to now once we run, we can see the output, and it looks beautiful. Look at that. So this is the frequency. This is the output, the plot for the FFT, and this is the signal. So if we're gonna zoom in here, so we can see the signal right here. So look at that. It looks like a pure sine wave, and the frequency should be. Let's zoom in here. Around 1200 hertz, and the reason it's not exactly 1000 is due to the rounding off. So if I go back to my table here, you can see it's around the phase increment should be 2.6214, and I'm setting it to 3, so I can't really get more accurate than this because of the way DDS is set up. You would have to play with it more to actually get it close, get exact 1000 hertz. You have to play with the DDS and make sure if it's possible to do that. And now let's do the second round, which will change the frequency now to I'm going to change the DDS frequency to 4K. So to do that, we're going to be changing the code. So let's go to where the code is located. Again, as I said, I am running. This is the code that is under revision control. But since I already imported data under my development folder, so it should be here. This is where I should make change. So this is where I change in order to see immediate impact on the output. So if I go to software development, FIR PL source. If I go to main, let's close out this main. This is the main that is under development. So if you make any change here, it will not be under revision control based on this folder structure, based on the way I'm working with division control in this design. So make sure the changes that you make in this if you make any changes in this folder, apply it to the folder that is under revision control. So we're going to change that to A. Let's go back to where is what am I looking for here? So yeah, looking for this. So if we change this to A, it will output a 4K hertz signal, hopefully, and that should be totally out of band, as we see in this frequency response of the filter. It should be around here, so we should probably see nothing at the output. If we see a beautiful waves, that means something is off. So let's go ahead and change this to A and save that. So we're going to save that, close that out. We're going to be rebuilding the app. Let's go back to a command line. So let's rebuild that because we made change. Again, before I even go there, you can see that this is the output of the 1K hertz signal processing. You can see that's 1K. And once we make a change, we should see that change to 4. Let me actually make sure I changed it here. Let me go back to the the main, and I changed the register value, but I did not change the printf, so I can see that the change was applied. So save that. That's set to 4K. Save. Close that out. And then I'll rebuild the app. There's a line to rebuild the app. I don't remember, so I just have to go back to my script and I copy and paste the line that does that. So let me go to a script that does that. So this line right here builds the app. Copy. Control V. So we're pretty much going to be rebuilding the app. So let's put the output of the board and this command line side by side so we can see what's going on. All right. Okay, now that looks good. So we're rebuilding the app. We're gonna run this and we're gonna see this change to 4K. And once we import new data, we should see nothing come out. So now we're going to be sourcing source run app. This will download first stage bootloader. It will download the initialize PS7 and download the application. So source run app. What happened there? I didn't see anything. Did I? Okay, I didn't see any change there, but here it is. And if we go to my printf, you can see the DDS output frequency was changed to 4K, so that means a change was applied. Now we're going to import the data to Matlab and see if the output is correct. So let's source, move that out of the way. Source read m.tcl. That should now replace the file. Let's close this out. Let's close that out. So that's old data. We're gonna get rid of it. Get rid of that. Get rid of that. We're gonna reopen with the new data. So let's clear our Matlab workspace so we can work in a new and clean workspace. So let's go to home, import this data. This data was just generated a few seconds ago with the 4 kilohertz signal. I'm gonna click open, control all, output type is string array, and import. And here is our data. So we're going to run, and look at this, garbage in, garbage out. So we pretty much have nothing at the output because we changed the frequency to something that is totally out of band. Yeah, so this is pretty much it, guys. So we can see that once you change the frequency of the DDS, you will have pretty much nothing. I didn't play with the magnitude of the FFT. I didn't have time for that, but you can go ahead and play with the amplitude and make sure how precise you are if you actually attenuated the signal 80 dB, or maybe you can even if I go back to the filter that I closed out. Where is the filter? Apps, filter designer. Let's open the session again. If you look at the frequency response, you can play with this further. You can put out, for example, 1K hertz and make sure it's not attenuated, and then you can even put out a frequency around maybe 2300 and see if it was attenuated around -40 dB, and then you can play with it, see how accurate, how does the filter perform more extensively. I'm not doing that. I didn't do that, but you are free to do that. The code is available. Even this small script file, Matlab, if you want to use Matlab. But if you can use some other tool to post-process this data, anything that can plot and compute FFT, and you can visually see what the signal looks like, you can use any other tool other than Matlab. But this is available to you if you're using the Matlab. And one other thing that I want to show you before I take off, what's the time here? Okay, I'm on 25 minutes, way over the time that I was aiming for. So I want to show you how to run this equation in Matlab. I have that under my system design document. So this system design document is available to you as well. If I go to my main folder structure, if I go to main folder structure and I go to document, system design is available to you there. You can see more detail about the system design. I also come here and talk about, for example, what's the FIFA 5. I keep going back and forth between the two. So this is the amount of data you gotta write into FIFA in order for it to trigger the full flag. I also have a line here that shows how to compute the increment in Matlab. I just run this code in Matlab, so I'll just show you. I should have a history of it there. So here it is. So that's the line right there. I have the frequency and everything else that's run, and you can even convert if you have some, let's say if you have some other number, if you want to compute, this is 25 megahertz, 1 2 that 1 2 3 1 2 3. If you want your frequency to be, for example, 10k hertz, you can easily change it that way. So this is fancy, like this tool is a fancy calculator. It's useful for this kind of stuff. So that's your number, and then just convert that number to hex, and then you're on your way. You can set it to, you can maybe do 20 megahertz, 20 kilohertz. Set 20 kilohertz, and that's your phase increment. All you gotta do is change that to hex, write it to the register, and you're well on the way. So guys, this is it. This is the last video that I'll be explaining how to set up this project. But what I'll do later, I have a video series coming up where I'll actually go in details about some of this stuff. Yeah, this video is just to give you a guide on how to set up the tools and environment, and quickly be on your way when you request this design and run it on your machine. But thanks for watching, and enjoy the design, and of course, as I always say, keep innovating.